Hello guys. So in this video, we're going to look at the electromagnetic spectrum. And so the learning objectives for today's video, we're going to identify the amplitude, the wavelength, and the frequency of a wave. We're also going to describe how the wavelength and the frequency compares for different regions of the electromagnetic spectrum. And then we're going to use the speed of light to convert between wavelength and frequency. So here we have an example of a wave, okay? So at the very top of a wave, we have what we call either a wave crest, or sometimes you hear it as called as a wave peak. All right, so this is your peak of the wave. At the very bottom, we have what we call the wave trough, okay? Now, from wave trough to the adjacent wave trough, all right, we have what we call the wave length, okay? And sometimes also we may have it to where we're measuring the wavelength from peak to peak. So this is also the wavelength. And really, you're just looking at the length from one trough to the next, or from one peak to the next. This center line that you see here, all right, this is kind of like the center of the wave. And so from the center to either the peak or even to the trough, because they're the same distance, we call that the amplitude of the wave. Okay, so just to quickly review this. So from the bottom of the waves, all right, the very tip, we call that wave trough. The very top, we have wave peaks or wave crest, all right? And now if you're going from the distance between one peak to the next, that's you have your wavelength. Same idea from one trough to the next, you that's your wavelength. They're the same length, same distance. And then from the center to the peak or to the trough, we have what we call our amplitude. All right, so when we're talking about waves, right? And so let's compare wave one with wave number two. All right. And so here is wave one. Here we got wave number two. Now, when we're talking about wavelength, remember wavelength is the distance between a wave peak to the next wave peak, or distance between wave trough to next wave trough. So when we're looking at this, all right, this right here is our wavelength, okay, of wave one. And so we use lambda to represent wave one, all right? Now, when you look at wave two, we notice with wave two, the wavelength is actually much smaller, okay? And so this kind of shows you that, different waves could have different wavelengths. Now, another aspect of waves that we typically care about or we typically like to measure is what we call frequency. All right. Now, frequency is the number of waves that pass a fixed point of unit time. So let's just assume that wave one and wave two are both in the same unit time. Okay. Now, if you notice, if we consider each one like a wave or like wave peaks or wave troughs, okay? We can see here in wave one, all right, the frequency is lower because you don't have as many waves that goes through in this standard unit time. Versus in wave two, we have a lot more waves during this unit of time. Okay. And so typically the unit of frequency, if you think about the number of waves per unit of time, is always going to be um, 1 over some time. Okay. Typically, in chemistry, we like frequency to be 1 per seconds. All right. Or we just call it hertz. All right. And hertz is essentially 1 per second. So it's the number of waves that passes through in a second. Okay. So hopefully you could see that both wavelength and frequency are inversely proportional, okay? And so what do I mean by this? So when we're looking at the wavelength of wave one, all right, you notice is longer than the wavelength of wave two. okay? But then at the same time, when you consider the frequency, all right, the frequency of wave one is actually lower than the frequency of wave two, all right? And so because remember, frequency is the number of wave that passes per unit time. And so we're just assuming that wave one and wave two is the same unit of time. And so we got less number of waves in wave one, so has a lower frequency versus wave two. There's more waves, so there's a higher frequency there. And so when you kind of look at this, that the higher the wavelength, the lower the frequency. All right. And the lower or the shorter the wavelength, the higher the frequency. All right. And so it just turns out that both wavelength and frequency has an inverse relationship to one another. Now, here is the electromagnetic spectrum. All right. So now the electromagnetic spectrum is the range of all possible frequencies or wavelengths, really, um, and wavelengths in the electromagnetic spectrum. It provides us a way for us to categorize the vast array of electromagnetic waves that occurs within the whole universe, from the lowest frequencies, like what you could find in the radio waves, and all the way to the highest frequencies, like gamma rays, which tend to ionize atoms. All right, and helping us to understand the electromagnetic spectrum is definitely very crucial in numerous different type of technological advancements, and it provides the foundation for fields like such as radio technology. We use it a lot in medicine, astronomy, and even oftentimes understanding the fundamental nature of universe. Okay, but the whole point here I wanted to show you with the electromagnetic spectrum is just the different subdivisions, right? And so the highest wavelengths and the lowest of the frequencies, we have your radio waves, and it kind of shows you about the relative size of these wavelengths. So radio waves are typically as tall as buildings, skyscrapers. Okay, so times 10 to the third meters. Okay. And then as we go across the electromagnetic spectrum with the highest wavelength, and as you move towards the right, we're decreasing the wavelength. So here you can kind of see this illustration showing this. We have the radio waves, microwaves, infrared, visible, ultraviolet, then X-rays, and then the one with the smallest wavelengths are your gamma rays. And so inversely, that's what's going on with frequency. So the one with the lowest frequency, all right, where we see times 10 to the fourth, all right, we have radio waves. And then as the frequency increases, we're going to microwaves, infrared, visible, ultraviolet, X-ray, and then the types of wave with the highest frequency are your gamma rays. All right, so it's going to be good to kind of just know this order and know it in the order of both increasing or decreasing wavelength and vice versa, increasing and decreasing frequency. And so experimentally, it has been found that electromagnetic radiation travels all at the same speed, especially in a vacuum. All right. And so there's this relationship or mathematical relationship that we have, where C is equal to wavelength times frequency. C is your speed of light. This is your constant. This is basically the conversion between wavelength and frequency. All right, so the speed here is 2.998 times 10 to the eighth meters per second. While we have wavelength, all right, wavelength is typically measured in meters, and especially if you're trying to use this equation here. And then frequency is measured in hertz or is 1 per second, or sometimes you see seconds to the -1 exponent. All right, and so let's do an example problem of how we could use this equation. So let's look at this example problem here. My friend Bob's favorite color of light is 454 nanometers. What is the frequency of this light? All right, so remember the conversion between frequency, all right, and wavelength is your speed of light, right? So C equals wavelength times frequency. Remember, C is 2.998 times 10 to the eighth meters per second. Okay. Now, one couple of things I want you to keep in mind, and I want you to make sure that we don't forget. Notice our wavelength is in nanometers, and oftentimes wavelength is measured in nanometers. But at the same time, you see the speed of light, the units is meters per seconds. So what that simply means is that we have to convert nanometers to meters. So the way I think about the conversion is that 1 nanometer is equal to 10 to the negative 9 meters. Okay, so that's the conversion between nanometers to meters. So if there are 454 nanometers, then it is 454 times 10 to the negative 9 meters. Okay. And so this is going to be the number that we're going to use to convert from wavelength to frequency. Okay. And so here's our equation here. Once again, I'm just kind of move this. All right. So if the speed of light is 2.998 times 10 to the eighth meters per second equals, and we know our frequency, I mean, our wavelength is 454 times 10 to the negative 9 meters, then all we have to do is solve for frequency, okay? And so we'll just divide by both sides. 554 times 10 to the negative 9 meters. This will cancel out. What you do to one side, you got to do to the other. Okay. And so now, when we're kind of looking at this, our frequency is 2.998 times 10 to the eighth meters per second over 454 times 10 to the negative 9 meters. And so when you put this in your calculator, you should get. So the answer to this will be 6.60 times 10 to the 14th hertz, or 1 over seconds. Okay, and so this is the way how you would solve for frequency.